Have you ever wondered if there's one single rule that governs everything? Something that applies just as well to a falling apple as it does to the orbit of an entire galaxy? Well, there is, and today we're going to unpack it. It's like nature's own perfectly kept unbreakable ledger.
So what is it? What is this one fundamental rule that can't be broken? It's a huge question, right? But the answer, well, it's actually incredibly simple. It all comes down to bookkeeping. Seriously, the universe is the most meticulous accountant you can imagine.
And that unbreakable rule is the conservation of energy. Think about it like a cosmic bank account. You have two main accounts: kinetic energy, which is the energy of motion, your spending money, and potential energy, the stored energy of where you are, your savings account. When an object falls, it's just moving funds. It cashes out its potential savings and converts it into kinetic spending money. The numbers change in each account, but the total balance, it never, ever changes. The books are always perfectly balanced.
Okay, so to really get our heads around this cosmic ledger, we're going to start with the most basic transaction you can possibly have: a single object just falling straight down. Simple as that. So, these are our two accounts. You've got kinetic energy, which we call T, that's the energy of doing something, of moving, and then you have potential energy, U, which is the energy that's just waiting. It's stored up because of an object's position, ready to be unleashed. And the law is incredibly elegant. T plus U, the sum of those two, has to stay constant, period. What's really cool is how this all connects back to the physics you already know, like Newton's laws. The speed at which an object's kinetic energy changes is something we call power. A good way to think of power is as the useful part of a force. It's the amount of push that's actually going in the same direction the object is already moving. And if you add up all that power over the whole trip, you get what's called work, which is just another name for the total change in kinetic energy.
Now, that all makes sense for a straight line, right? But what happens when the path gets a little messier? A bit more complicated? What if it's not a straight shot down?
So let's look at a little puzzle. You've got two identical balls. They both start at the exact same height, and they're going to end at the exact same height. But one takes the direct route, while the other goes on this loopy, winding roller coaster track. Let's assume there's no friction. Which ball do you think has more kinetic energy, more speed, when it gets to the finish line? And the answer is neither. It's a trick question. Their final kinetic energy is precisely the same. That whole wild roller coaster ride, it made absolutely no difference to the final result. And here's why. It's because gravity is what physicists call a conservative force. And that's a fancy way of saying the work it does is path independent. Gravity doesn't care about the scenic route. It only cares about where you started and where you ended up, specifically the change in your vertical height. All those sideways twists and turns, they all cancel each other out in the final calculation. And this leads to an incredibly profound truth. If you could build any kind of frictionless track that loops back to where it started, the total work done by gravity over that whole trip would be exactly zero. You can't cheat it. And that is the deep, fundamental reason why perpetual motion machines are impossible. You just can't extract free energy from a gravitational field. The ledger always balances back to zero at the end of the day. All right, let's zoom out, way out. We need to see how this ledger works on a cosmic scale. See, here on Earth, we can pretty much pretend gravity is a constant force. But when you're talking about planets and satellites, that idea completely falls apart. It's time for a galactic audit. Out in the vastness of space, gravity isn't this constant thing. It gets weaker with the square of the distance. So to figure out potential energy, we have to use calculus to add up that changing force over huge distances. And what pops out is this new, more universal formula. Now, you might be wondering, why is it negative? Well, it's just a convention. Physicists define zero potential energy as being infinitely far away from everything. So, if you're gravitationally bound to something, you actually have less than zero energy. But don't worry, it works the exact same way in our cosmic ledger. So how in the world does this work for something like a whole solar system? You've got all these objects pulling on each other. It sounds like a nightmare to calculate, right? Well, there's a beautiful principle called superposition that makes it manageable. You calculate the total energy in two big steps. First, you just add up the individual kinetic energy of every single object. Easy enough. Then, you add up the potential energy that exists between every single unique pair of objects in that system. It's a huge sum, for sure, but the logic holds up perfectly. To make that feel a bit more real, just imagine you're building a solar system from scratch.
You grab your first mass from infinitely far away and place it. That costs you nothing since there's no gravity to fight against yet. Then you bring in the second mass. Now you have to do some work against the pull of the first one. Then you bring in a third. Now you have to do work against the first one and the second one, independently. The total energy stored in your brand new system is just the sum of all that work you had to do to assemble it.
And this brings us to our final stop, and honestly, it might be the most elegant idea of all. We're going to look at these strange, almost magical rules that pop up just from the way mass is arranged in space, the geometry of gravity itself. This is called the shell theorem, and frankly, it feels like a mathematical miracle. It says that if you are outside a perfect sphere of mass, like a planet, the gravitational pull you feel is exactly the same as if all of that planet's mass were squeezed down into a tiny single point right at its center. This little trick is the reason our simple formulas for orbits actually work so incredibly well. But here's where it gets really mind-bending. What if you go inside that hollow shell? The net gravitational force on you drops to zero. Nothing. How is that possible? Well, look at the diagram. The super strong pull from the little bit of mass that's close to you is perfectly, and I mean perfectly, canceled out by the weaker but much more plentiful mass on the far side of the shell. The forces all balance out, which means the potential energy is the same everywhere inside. And if potential energy doesn't change, no work can be done, which means no force exists. It's a perfect little pocket of 0G. Okay, so we've gone from simple falling objects to planets to the very structure of stars. And we've seen this one single principle show up again and again. Let's pull it all together into one unified framework. Just look at this table. It really lays it all out. Whether you're talking about an object falling near Earth, a planet orbiting the sun, or even something totally different, like a mass on a spring, the underlying logic is identical. Yeah, the specific formula for the force changes, and that means the formula for the potential energy changes, but that core rule, that the total energy is conserved, that stays completely unbreakable. And that's really the big idea here. From the smallest scales to the largest, the universe is fundamentally running on this one simple equation. Energy is constantly changing its form, trading kinetic for potential and back again, but that total amount in the cosmic ledger, it stays perfectly, beautifully, unshakably constant. So today, we've really uncovered the architectural principles of the cosmos. We've seen the deep connection between power and work. We've understood the critical importance of path independence for forces like gravity. We've seen how superposition lets us calculate the energy of incredibly complex systems. And we've explored the weird and wonderful geometry of mass. And every single one of those ideas flows directly from that one simple, unbroken rule. And that kind of leaves us with a final, bigger thought. If forces tell an object where to go from moment to moment, then energy conservation is what sets the rules of the game. It doesn't dictate the specific path, but it sets the absolute budget for the entire trip. It defines the very boundary of what is possible. So it makes you wonder, what other parts of our universe, maybe not even in physics, are governed not by moment-to-moment directions, but by some kind of unbreakable cosmic budget?